Good morning, everyone. Welcome to the Toronto Geometry Colloquium Season 2. This is a weekly series all about geometry processing.
This colloquium aims at promoting young researchers and researchers from traditionally underrepresented communities. Every week, we will have an opener talking about their cutting-edge research for 10 minutes, followed by a headliner giving us a keynote presentation.
Today, we are thrilled to have Emmanuel Yarusi as our opener to talk about generating 3D bone microstructure, and Elisa Ross as our headliner to talk about applications of lattice geometry. Our first speaker today is Dr. Emmanuel Yarusi, a scientist at the Argentinian National Scientific Research Council. He got his PhD at INRIA Sophia Antipolis in France and was a postdoctoral researcher at IST Austria. His research interests are really diverse, from tools to aid drawing for artists and surface design, to improving the quality of medical ultrasounds and learning to detect cancer cells, and basically everything that is between those two extremes. Apart from his amazing research work, I'm also very inspired personally by the effort that Dr. Yarusi puts into communicating science and data to the very often neglected Spanish-speaking world. An effort that has been especially relevant as we have all been staring at infection and vaccination data for over a year now. Fun fact, he's even been on Argentinian TV. You can see that pinned on his Twitter profile. So without further ado, let's all welcome Dr. Emmanuel Yarusi. You're muted, Emmanuel.
Sorry, yeah, thank you, Silvia, for that great presentation. I'm thrilled for it. I'm sharing my screen now, and let me know if you see it. That's right. Can you see my video and my screen?
Yep, all working.
Okay, so thank you very much for that very nice introduction. I'm super happy to be here today. I'm a big fan of the colloquium, so I will first like to thank the organizers for the invitation. It's really a pleasure to me to be presenting here today. And I would also like to acknowledge Felix Thompson and Claudio Del Rio, which are the co-authors of this project, which is entitled Learning to Generate Realistic 3D Bone Microstructure with Controllable Parameters. The funding for this project mainly came from the National Scientific and Technical Research Council, CONICET, which is the main public science institution in Argentina. And the work I'm presenting today is a paper we published last year at MICAI. And for those who are not very familiar with the medical imaging journals and conferences, MICAI is a huge annual event with 1,000 attendees, mainly world-leading biomedical scientists, engineers, and clinicians from a wide range of disciplines associated with medical imaging and computer-assisted intervention. I would also like to mention that after the publication, we applied and won one of the 6 annual Salesforce AI research grants, and in direct competition with more than 180 proposals from over 30 countries in the world. So we are super happy for this funding, which will allow us to continue to develop the main ideas I'm presenting here today. Research in vertebral bone microstructure often requires expensive and very time-consuming procedures to obtain physical scans of real bone with the pathology under study. The main technology used to get images from bone is a high-resolution computer tomography, also known as CT. And in order to get volumetric images from the bone, you first need to clean it and dry it. And it will only be ready to hit the CT scanner after you embed it into epoxy resin. After the scan, and as a post-process, the spongy part of the bone has to be peeled off from the cortex, usually with a semi-automatic procedure. And sometimes you also have to downsample it in order to increase the signal-to-noise ratio. This is often a very tedious and complex procedure, which could be avoided, especially if virtual synthetic models of bone are made available. For instance, in structural and resistance analysis, some researchers have proposed simple bone models consisting only of a few rods and plates intersecting each other. Even if these synthetic virtual models allow easy control of the target output, they often oversimplify the geometric structure of bone, which actually looks more like this, or also this. In the context of computer graphics, several procedural techniques have been recently proposed to synthesize and control the deformation properties of fiber-like microstructures, to be additively manufactured. However, for medical applications, the design of fine and detailed geometry that mimic realistic bone requires to have real human data into account. We therefore developed a direct method to create 3D microstructural bone samples that first contain realistic structures similar to those in a bone scan dataset, and second, allow to steer the properties to simulate changes from deterioration or medical bone treatment. So we want to be able to synthesize bone samples, but we also want to, we are specifically interested in computed and offer user control over well-known microstructural measurements commonly used in medical studies. First, the bone mineral density, which is the average density of the input volume X and its corresponding standard deviation. Also, the bone volume ratio, consisting in a ratio of bone to total volume when segmented with a threshold T. And finally, the tissue mineral density, which is the density of the segmented bone. In order to synthesize bone samples, we rely on generative adversarial networks, which are trained to stochastically generate samples close to the distribution represented by a training set. In particular, we train a generator network to map random noise to 3D volumes that look realistic, while a second network, the discriminator, learns to distinguish fakes from real samples. Our training dataset consists of 12 human vertebrae scanned on a high-resolution CT. We subdivide these volumes to get almost 8,000 patches of 32 voxel size and augmented them with 16 axis-aligned rotations and reflections, respecting the longitudinal anisotropy of form. And for the neural networks, we adapted 2D state-of-the-art generative models to handle 3D data and implemented several training schemes: a vanilla GAN, a Boston GAN with gradient penalty, and a progressive growing GAN. After training, we compared the random generated volumes against the real samples in our dataset in terms of microstructural parameter distributions. Since these parameters are not fully independent from each other, for simplicity, we reduce the space to two linearly independent principal components in the slides PC1 and PC2, which explain 99% of the variation on real patches. The vanilla GAN was able to generate visually appealing bone patches, but the parameters diversity was narrow in comparison with the real distribution. In contrast, both Wasserstein GAN's architecture were able to produce visually good results while covering a larger area in parameter space. Besides that, all neural networks underpopulated certain areas in parameter space, the progressive Wasserstein GAN generated patches that were visually most difficult to distinguish from the real ones. And in quantitative terms, only the progressive GAN was indistinguishable on all considered metrics. If you want more details, you can go to the paper for them. And a key ingredient in our pipeline is to allow user control of the sample generation. And in order to achieve this, we draw inspiration from style transfer techniques, which have been largely used in other contexts to transfer style between image pairs with preserving its content. We therefore frame an optimization problem over the latent space of our trained generative model. In the spirit of style transfer techniques, we define the content as the target volume we want to stick to provide the general structure constraint in our optimization. The target volume can be a sample from a training dataset or also a random volume produced by our generated network. For the second term, we redefine the notion of style for 3D scans of human bone. In our context, the term style refers to a given set of microstructural properties that our generated sample has to satisfy. The optimization aims to find a vector Z prime in this latent space, compromising the content and the style goals. Notice that in order to minimize this objective, the operator P, which computes the set of parameters over the volumes, has to be differentiable. And that's the reason why we derive new differential formulas for the bone volume ratio and the tissue and mineral density parameters. We achieve the smoothness by defining parameters that are strictly monotone in T, and define a function, a soft-pass function, which is parameterized with a fuzziness factor epsilon in order to replace the crisp threshold operator. More details on this can be found in the appendix of our paper. Thanks to this formulation, we achieve full control over the microstructural properties when generating new samples. The figure on the left shows the application of the neural style transfer method to generate 25 bone samples with slightly different microstructural parameters, All patches are a smooth variation in parameter space of the center patch. In this example, we kept the structure as fixed as possible while simultaneously fitting the individual target structural parameters. On the right, you can see two generated samples from extreme opposites in parameter space. We foresee our method being useful in a number of applications, like the simulation of microstructural changes by bone-forming drugs or in mobility. For instance, the structural properties of specific osteoporosis treatments have been measured, and therefore our contact preserver method can be used to simulate bone after specific treatment. On the screen, we show our simulated bone under two drugs, residuronate and teriparatide treatments after 6 and 18 months. While residuronate on the left is known to mainly calcify existing bone, teriparatide on the right is able to form new bone. Our simulated microstructure may also serve to compute minimum bone failure, often requiring exact models of bone. In the future, we want to increase the size of our training dataset, and in this direction, we have now a running collaboration with the Calgary University to provide us with more XCT scans from human bone. We also want to enlarge the size of the synthesized volumes, because when training GAN networks, we notice that the patch size can make the difference between a successful model and a mod collapse one. Ultimately, we want to be able to increase the resolution to generate an entire vertex. Finally, we aim to apply these ideas to areas beyond the medical field, like the microstructural fabrication for the formable 3D prints that I've shown at the beginning of this talk. Well, thank you very much for your attention. And remember that all the code and data I've mentioned during this talk is freely available on our GitHub repository, where you will also find more examples and information about the project. Thank you very much.
Thank you, Emmanuel. That was a really eye-opening presentation on a very interesting topic. As we usually do, we'll now move on to our headliners talk, and we'll have a joint Q&A for both at the end. As a reminder to our viewers, you can put your questions either on our Discord or on our YouTube chat, and we'll ask them ourselves to the speakers at the end. Okay, so now let's move on to Dr. Elisa Ross, who is a mathematician working as a partner and scientific lead of Mesh Inc., a Toronto-based consultancy. She is also the CEO of Metafold, I'm assuming that's how you pronounce it, a large-scale 3D printing company for industrial applications. Much like our first speakers, her work is incredibly diverse, and it is unified by the connecting thread of finding interesting mathematical problems in real-world applications, be it managing uncertainty in architecture, material design, the price of home renovations in the city of Toronto for some reason, or making accurate yet modern mathematical illustrations in publications. So again, a very wide range. We are also, in particular, really excited to be hosting Dr. Ross at our colloquium. She brings a perspective that not many of us in academia have. She is the breathing, living, talking image of interdisciplinarity, having worked side by side with architects, artists, engineers, mathematicians, geologists, physicists, and computer scientists. She's also the first Toronto born and raised speaker of our Toronto Geometry Colloquium, which means that after 2 seasons, we're more or less presenting an accurate distribution of where people living in Toronto have been born. So let's all give a warm welcome to Dr. Elisa Ross.
Great, thank you so much. And let me just share my screen with you here. Okay, so let me see. All right, hopefully you are seeing my slides. Awesome.
We are.
Okay, great. Thank you so much. And thank you, Sylvia, for a very kind introduction, and to all the organizers for the invitation to speak and this great initiative. I really love this initiative. And yeah, it's a great joy to be here. And I'm really excited today, as Sylvia mentioned in the introduction, I kind of currently have 2 roles in my professional life. One is as a consultant at Mesh Consultants, and the other is as a co-founder of a new startup, which is a spin-off of Mesh, but is nevertheless a separate thing. And so actually today I want to give kind of 2 mini talks, one from each of those roles. And the linking theme is, before I kind of get into what those talks are, the linking theme for both of them is lattice geometry. So before I start those topics, I want to try to motivate this with the question, why should we care about lattices? And to do this, I want to take a very zoomed out look. I want to talk about material property space. So materials, of course, are all around us: wood, glass, metals, all kinds of things, plastics. And there are all kinds of properties that these materials have. So they might have a particular strength or density. They might be brittle or tough. They have a certain Young's modulus. They may have certain electrical properties. I mean, there's a very long list of things you might care about in terms of material properties. So Michael Ashby is a professor at the University of Cambridge, and he came up with this idea of kind of taking a slice through material property space. So you take any two properties and you plot them against one another, and then you get this picture of different materials and how they sit relative to one another. So zooming back in time, I guess, back to prehistory, to 500,000 BCE, this is a picture of what materials our human ancestors had available to them at that time. So we see all the natural materials, things like bone and shell and antler, and they also had gold. And then we progress forward. This is around the time of the Roman Empire. And you can see that there's been some significant changes, especially in the domain of metals. They've also added concrete and glass, which is very significant. What I find quite interesting, though, is that from this picture up to 1945, so there's been some significant change. We see some new alloys and notably the addition of polymers, so plastics, but it's not that different. And compare that with present day, where we have this kind of explosion of materials. So the question is, there's still a lot of white space on this chart. And the question is, how do we fill that space? How do we find materials to cover this breadth of material properties? Now, I should say the kind of corners here are inaccessible due to kind of fundamental properties of matter, the size of atoms and the nature of the forces that bond them together. But there's still a lot of white space kind of adjacent to the materials that we know. How do we push into those areas? There are kind of two strategies to do this. The first is through chemistry, but I believe it's the opinion of people like Michael Ashby anyway, that this has been fairly well explored at this point, and future changes in this area are more likely to be incremental than they are to be stepwise. Whereas the other strategy we can use to fill material properties is through looking at geometry or architecture. So, and here I mean architecture at a very small scale. So really kind of controlling microstructure, much like in Emmanuel's talk. So this offers new potential. And that brings me to this picture. So this is the same picture, but now we've got these long finger-like regions. And you can see this one, for example, this is carbon fiber reinforced polymer. And the finger kind of begins at this dot at carbon fiber reinforced polymer, and then it expands this way. And the reason for this coverage is geometry. So this is the result of being the geometry of that material. So it's kind of actually, you can think about this in the context of 3D printing. 3D printing will spit out a certain material, but then you can get different material properties by changing the geometry of what you print. So this is why we should care about lattices. All right, this brings me to the outline for my talk, which, as I said, has these two parts. One is about prediction, how we work lattice geometry from a design side, and this is a mesh consultant's topic. And then on the other side, I have a validation topic. Using this term a little bit loosely, what I really mean is just producing physical objects, and that is the metafold part. Okay, so in the first part here, I want to talk about some recent work. This is joint work with my business partner at Mesh, Daniel Hambleton. This is going to be appearing in Advances in Architectural Geometry 2020, which is actually happening next month. But the topic of this is using graph neural networks to approximate mechanical response on lattice structures. So to get going, actually, I thought I would just say a brief word about mesh, because I think that provides an important context for this work. So our tagline at Mesh is solving critical geometry problems in industry. And I think you all know what geometry problems are, but just to unpack the critical and industry part, we tend to get called when people have kind of reached the limit often of their software and what it will do in terms of tackling some kind of real geometric challenge. So we do work in a variety of areas from architecture through engineering. We tend to do a lot of software development, source code development. Unfortunately, a lot of our project we're also under NDA, so we don't get to talk about so much of that. But we also have a strong research and development mandate, which is what I can talk about today. Let's talk about some of the actual challenges with working with lattices. So we've motivated the idea that lattices are really cool and we want to use them, but how do we actually do that? The first challenge is just a selection challenge. There's this vast, infinite space, in fact, of possible 3D lattices. How do we actually select one for a particular application? And typically this means we're looking for something with a particular performance metric that's going to hit some material property we're interested in. But how do we actually how do we search that space? The answer to that usually rests on simulation. So we would take these structures and do some kind of simulation to detect their material property. But this is actually quite challenging. That this is usually done by finite element analysis. There are certain kind of lightweight forms we can use, but they tend to be lower fidelity, and want to move to a more accurate simulation. It gets very difficult because of the complexity of the geometry. So this makes that whole process very, very slow. Our question was, is there something we can do here using machine learning in a predictive way? Can we use machine learning to predict the effect of compressive forces or geometric deformation on lattice performance? This can be thought of as the structure property relationship for lattices. So we have a lattice, we're interested in learning about its stiffness, and we want to use machine learning as a surrogate for finite element analysis. So the current approach is quite slow and expensive, and the question is, will machine learning have something to say here that will be more useful? Of course, there are significant challenges to this. So a typical machine learning model ingests only flat or Euclidean data, whereas lattice data is by definition heterogeneous. We may have different numbers of nodes and edges. And also typical models require data that is invariant to transformations, whereas lattice data is inherently geometric in 3D. So the usual techniques that work in 2 dimensions to tackle this become much more computationally problematic or just time-consuming and expensive in 3 dimensions. That leads to the topic of graph neural networks, which are well suited for this type of lattice because what I'm talking about right now are lattices that are graph-like. You can think of them as embedded graphs. So what is a graph neural network? Essentially, I'm not going to give much detail here, but essentially a graph neural network generalizes the methods of deep learning to graph structured data. And I think this picture is really illuminating. You can think of Euclidean data, you can actually think of it as a graph, but a very, very structured and orderly graph where we know exactly what the neighbors of any given point are. Whereas graph structured data is much more heterogeneous. We don't necessarily have the same number of neighbors for every node, and there's just a lot more uncertainty. So here I'm really talking about the idea of trying to generalize convolutional neural networks to a graph domain. But the goal of graph neural networks remains the same, which is to learn some highly nonlinear function given some data set. And I guess it's worth noting here that the typical tasks that GNNs are used for are things like graph regression and classification, which is what I'm going to be talking about, but they're also used I guess they come up in a wide variety of applications because there's so much graph structure data in the world. But they get used for things like node classification and link prediction in very, very large graphs, like the graph of a social network or the graph of the internet or whatever it may be. Whereas our application, we're going to be looking at smaller graphs. In terms of related work, we were really inspired by this paper, Neural Message Passing for Quantum Chemistry. So in this paper, the authors are looking at the application of graph neural nets to molecular structure. And they're actually doing something very similar in a way to what we're doing. They're taking a molecule and they're trying to learn this density functional theory, which is a simulation methodology. And so it's similar in a number of ways. The molecules are kind of small graph, and they're trying to come up with a surrogate for a simulation method. In a very simplified way, I can describe the graph neural networks like this. You can think of them as message passing networks, where each node has features, and then these features can be thought of as messages, and they're aggregated or passed in the according to the connectivity of the graph. And then the deeper your neural net, the more layers you add, the farther and farther away you're incorporating these messages from. And this is a nice model. It's implemented in PyTorch Geometric, which is a really nice graph neural network library for PyTorch, which has all the things you might want. Okay, so that's the graph neural network aspect. And so how about the lattices? How do we kind of, how do we think about these lattice geometries? So again, in a related work, we've been looking at this paper for many years. I keep coming back to it, actually. I really love this paper, Elastic Textures for Additive Fabrication. So in this paper, the authors come up with this family of lattices that can tile together and have unique physical material properties. And actually, here's one of these material property plots that I was mentioning earlier, and you can see they have lattices that correspond to different places on that plot. One thing the authors do, though, is they give a really nice way of recording lattices and generating a large data set of lattices. So we use the same method. And so generally speaking, we can think of lattices as being built from unit cells. A unit cell is a recipe for a lattice in the sense that it is, I guess you can think of it as the quotient of some kind of repetitive network under the three translational symmetries of 3 space. But what Panetta and his co-authors observe is that we can also take a smaller representation by taking a further quotient if we're looking at cubic lattices. So cubic lattice will have all the symmetries of the cube. And so we can quotient out by the symmetry group of the cube, and then we end up with these tetrahedra, the cube broken into these 48 tetrahedra, and we can define the lattice as just what geometry appears in one of those tetrahedra. Like many problems in discrete geometry, lattice data has a combinatorial element and a geometric element. On the combinatorial side, we're just asking what is the graph of the lattice, or what is the graph of the lattice pattern in this case, the smallest unit that's going to capture the lattice. And you can place nodes on the vertices, on the edges, on the faces, and they're going to have different degrees of freedom depending on where they're placed. On the geometric side, we're saying, okay, where are those nodes in space? And we can capture this by basically using ratios or offsets, as we're calling them, which say in this picture where the node is along that edge. So in other words, a lattice is going to be described by this abstract graph that represents its geometry in the tetrahedron, together with these offsets that tell us exactly where it's placed, tell us the embedding. Using that idea, we were able to create several very large data sets of lattices. There's certain criteria we want to guarantee. We want to make sure they're connected, and we want to restrict the node valence just to make sure we don't have like these incredibly dense lattices. But once we did that, we created these 3 different lattice data sets The first one was a mix of different combinatorial types. And just to kind of manage expectations, we found that this one just wasn't successful at all, which led us to creating these other data sets, which were much more focused. So in these other data sets, we have just one combinatorial type, and then we sample the geometric space quite densely. And we also did a version of that where we applied an arbitrary box morph to each of the items in the single type data set. So we end up with this kind of like deformed geometry. Okay, so we're almost there. We have our lattice data sets. And now the question is, what about the simulation? So we did a kind of lightweight simulation. We used the solver in Rhino and Grasshopper using the Kangaroo plugin. And we just took a measurement of the heights of the bounding box before and after the simulation. So it's not a super high fidelity simulation, that's for sure, but we really just wanted to create some kind of simulation result, some kind of black box that we could then figure out whether this approach would be successful or not. In terms of the actual machine learning model, as I said, we use the model from this quantum chemistry paper. So that's really not where the innovative part of this work is coming from. We pretty much use that right out of the box, which is a little tinkering. What is interesting is the way we represent data. And here we have a lot of choice. So just starting from the beginning, we start with a lattice, we represent the data, feed it into this graph neural network. There's some kind of readout on the nodes, which are then pooled to give us the compression target in the end. So, okay, so I want to just mention this data representation. So as I said, these lattices all have a combinatorial and a geometric element. For the combinatorial part, so graph neural networks are extremely convenient because they accept an adjacency matrix as an input, and it doesn't even need to be the same size. So we have a lot of flexibility, but there's a question, which is what graph actually do we want to use? Do we want to use this tiny lattice pattern that I was mentioning? Do we want to use the full unit cell? Do we want to use a larger chunk of lattice, which is also possible? Or we hit on this definition, which kind of seemed to be quite successful, where you identify the vertices on opposing sides of your unit cell that would be mapped to one another under the periodic symmetry. So we're calling that the merge boundary, and that kind of captures the periodicity of the lattice. On the geometric side, we also have choice here. So we can't use position directly because it would just require too much data to kind of capture all the different possible embeddings, but we can use either those offsets, those ratios that I described, because those are independent of the embedding, or we can try and use some kind of geometric features that capture the kind of local stiffness of the node. So we tried both things. And I should also that quantum chemistry model also relies on edge features. So we use both node features and edge features. Okay. So where did we get to with this? So as I mentioned, this kind of mixed data set where we have a whole bunch of different combinatorial types just simply didn't learn very much. I learned a little bit, but not very much. Whereas the ones that were more restricted, where we sampled more densely in the geometric setting, were much more successful. And as you can see, we tried a whole bunch of different representations. And this merge boundary together with the offset data seems to be kind of the best performer here. But I do want to highlight that it was interesting to see that it didn't actually rely on such a dense sample, that we used 25,000 samples, but we found that we could actually reduce this to a smaller data set without a huge reduction in the quality of the results. So summarizing the accuracy here, we ended up with an over 92% accuracy on those one type data sets. And then the morph data set is a little bit different. You can no longer use the offsets because you have to use the geometric features because it's no longer symmetric, but that's slightly less accurate. Okay, so how might we want to use this? The idea is that we might start with some kind of lattice structure that's populated on or around some kind of volume. And maybe that design volume is being pushed or pulled, and we are interested in getting predictions of relative compressibility of the lattices. And so we can actually do this. So the question is, are the lattice units more or less stiff than the undeformed case? So it doesn't give us a prediction about the aggregate behavior. So it's not like a surrogate for finite element analysis on this whole thing, but it at least offers us this understanding of areas of relative strength or weakness. And so just to say something about the colors, the yellow represents the same compression as the undeformed version. The green is half as compressive, so these are stiffer. And the red is 1.5 times as compressive, so these are softer. And here's another variation on the geometry. Okay, so where did we get to with this? So I think to summarize the contributions here, this is the first instance that I know of material properties being predicted from lattice geometry in this way. There's some, we use the graph neural networks to capture the lattice geometry and combinatorics. There's a lot of room for figuring out those hyperparameters more, say. And this offers the potential of real-time structural feedback for designers with the cost of finite element analysis. So this is kind of the performance-aware design idea. And it's worth saying that this is, despite how densely we did have to sample to get those results, it also really outperforms a kind of lookup or interpolation approach, which would just require so many more data points for similar quality results. There's no good way of capturing what the appropriate distance metric would be on the space of lattices or lattice features. So, or at least I don't know of one. So it seems like this is actually kind of has some potential for that application. And in terms of next steps, okay, so I've mentioned the idea already of creating a higher fidelity simulation. Also, the success we had with smaller data sets suggests that we could build up a larger data set with many combinatorial types that had 2 or so thousand geometric samples per type, and that could be a more successful data set. But one way we could imagine using this is kind of almost like that Panetta paper I mentioned in the beginning, that you could create a little library of lattices that you were interested in using and train a model on each of those lattices, and then use that trained model to really get an awareness into the design phase. First, the kind of holy grail of these sorts of problems is the inverse problem, and this is what Emmanuel was talking about, which is so cool. But here you input a compression target, and then you output a lattice. And the challenge here is that lattices have so many design parameters that it's really hard to imagine how that would come out of such a model. Although I am hopeful for this because some of our best performing models did use offsets as their geometric features, and offsets are kind of like a recipe for a lattice. Okay, so that was part one. That was the kind of prediction part. I sort of zoomed through that because I wanted to get to part two, which I'm super excited about. And this is the validation part where I'm really talking about producing things. And so what I want to tell you about is a new 3D printing technology that we built specifically for lattices and metamaterials. And so this is really informed by the work of the previous section and some of the challenges I already mentioned about working with lattices. Our tagline at Metafold is "Shape Matters." I hope I'll be able to kind of communicate to you why we think that. And before I start, I just want to acknowledge that this project is definitely one of it is the most significant research and development project we've undertaken at Mesh, and it's absolutely a team effort. So I'm feeling super lucky to be here talking about it, but I'm also, you know, it's absolutely a team effort. It's really kind of Daniel and Tom putting together hardware and software that results in this work. So as an outline of this part of the talk, I'm going to give some motivations for why we created this, talk about our solution, which is called Light Cycle, show you a bunch of sample geometries. There's a few on screen right now as well. And then I want to end with a kind of vision and also an invitation. I believe I've already probably motivated this through the first part of the talk, but just to say a little more. So Mesh has been around since 2012. We've been applying mathematics to topics in architecture, engineering, and industry. We've worked on a variety of projects, including one project in predictive geology, where we were looking at really dense and challenging microstructure geometries. Since 2017, we've been on a sportswear contract. And here the idea is our client is really interested in using metamaterials to enhance human performance. So, and a lot of the things I've mentioned about lattice geometry and why they're challenging comes up in that project. Now, 2020 happened. 2020 was a year like no other, and like many small businesses, Mesh had a slowdown in work, and we took the opportunity to do this research and development work. And we have a kind of unusual team. So Sylvia mentioned interdisciplinary work in the introduction, and it's true that our team is a really kind of unusual. We've got mathematicians, architects, computational fabrication people, and these hardcore C++ developers all together. And so what comes out of that? And the answer in this case is this 3D printing technology. Okay, so what is a metamaterial? So actually my favorite example of a metamaterial is just a piece of paper. So we all know what a piece of paper is like. We know what it feels like, what its properties are like. It's very floppy. But we can also probably visualize this, that if you put an accordion fold in a piece of paper, you can set it down on your desk, it will actually stand up. And so suddenly, through changing the geometry of the paper, you've given it these different material properties. You've given it more structural rigidity. So that's the basic idea of a metamaterial, and specifically a mechanical metamaterial, where we're using geometry to extract some kind of performance. And this comes up all over the place. So things like lightweighting. The aerospace industry is always on a search for super high strength and super light materials. So they're very interested in metamaterials. Also for like protective equipment, like hockey helmets or footwear, or apparently spacecraft that need to resist ballistic impacts. These can be a really useful way of obtaining that. So yeah, as I said, we've made observations through our role as industrial consultants. And one of the main observations is just that the speed of developing new metamaterials and working with lattices is very slow. And it's the whole design process, print, validate. It just takes a really long time. And you know, there's been this kind of idea of additive manufacturing, this promise of additive manufacturing, that it's this very materially efficient and sustainable technology where you get geometric complexity for free. And our observation is that doesn't really seem to be true, that at a certain point of geometric complexity, it actually is no longer free. It's challenging, if not impossible. So we were really interested in printing those things that are so geometrically challenging that other print systems can't tackle them. The solution that we came up with, we're calling Light Cycle. And the basic thing we do is we print very highly detailed and complex geometries in large print volumes. So we specifically built it to print lattices and microstructures, where the features are really not well captured in traditional file formats like STLs or any other format that you might want to save these things out to. We're taking a more data-driven approach to 3D printing. So we kind of we skip that whole STL step and allow you to print directly from things like lightweight lattice specifications, implicit functions, point clouds, data streams, the results of Emmanuel's amazing bone simulation. We could print directly from those things without needing to create a surface mesh and save it out and slice it and all that stuff. The way we do this is by generating geometry on the fly. So we generate geometry in real time, and you can think of it as real-time slicing. And this is facilitated by a closed loop system where we have a very tight integration between the software and hardware, which allow us to always be reading feedback from the machine into the software. And we create the geometry kind of just in time for printing. But it also opens up a lot of opportunity for things like in situ error correction or monitoring the print health as you're printing. Okay, this is a kind of, I guess, kind of a cheesy render, but I think it gives you the idea of what we're doing. We have a projector, it's shining a light, and the light is moving across some build volume. So more concretely, here are some schematics. These are all DLP, it's a DLP system. So a DLP system involves a vat of photosensitive resin, and then you project an image on the bottom of the vat to cure a slice of the geometry, and then you build up a three-dimensional shape slice by slice in this way. And I think this one here kind of tells the full story that we have a projector on a linear rail, it slides across, and as it slides, it's curing this geometry. A key idea is that we're not trying to store all of the geometry in memory. Like, we're not trying to store the whole shape that we're printing. We're only generating the geometry we need as we need it. And the other cool thing about this is that we're using standard projectors. So we're using right now a standard 1920 by 1080 2K projector, but you could amp this up to a 4K projector to get higher resolutions, or eventually the 8K projector. So the only real limitation on the print resolution is the resolution of that printer, but we mount that on these linear rails to get even bigger build volumes. Okay, so now I want to show you some of the things that we have printed in this way. We have this vast, or we have a reasonably large, it's not vast, but a reasonably large library of Tpms structures. These are triply periodic minimal surfaces. These are really nice structures. They're different from the ones in the earlier part of my talk because they're surface-based as opposed to beam-based, but they have this property that they are locally minimizing surface area. And they're also really nice because they're well approximated by Fourier approximations. And so they have this really nice representation as just like a single equation, a single line of code. And so all of these things are really literally just a single line of code with the build space parameters. They also have this really nice range of material properties. This one is really cool actually because this bottom structure here is almost like a very stiff foam, whereas the top one is extremely soft so that you actually, when you press it down, it actually stays compressed after you release your hand. And some of the other ones are incredibly rigid despite being printed with very flexible resin. They're also just very satisfying and extremely kind of beautiful forms that I think triply periodic minimal surfaces are kind of having a bit of a moment. They're being used a lot, but they tend to be, there tend to be like a fairly narrow window of them that are used, whereas there are a whole bunch of them that are really fascinating, and we've been enjoying printing them. One of the maybe better known TPMS geometries is the gyroid. And so this is really a funny thing. So when we printed this, I mean, when you can see in the center that when you print it, it actually reads like a solid, like you pick it up and it feels like a textured surface as opposed to a porous solid. But in certain, certain angles, the thing is actually almost invisible, which was truly mind-blowing when we first printed it. It's this solid that becomes invisible under certain light conditions. As you can see, this is a really fine print. And what's significant here is that like each of these little dots is you can think of this as a lattice unit cell. So to my knowledge anyway, other printing methodologies can print hundreds and maybe thousands of unit cells. But with our technique, we can print millions or tens of millions at this point. So it's really several orders of magnitude different. We are also really excited about the prospect of printing fabric type geometry. So this is a chainmail. This was honestly a very kind of quick test, but we feel like it has some promise. And in particular, the fact that we use a DLP means that this is very fast because we cure a layer at a time, and we're doing it so we can just basically, it's only a few layers thick, and we can just do it very quickly. But also eventually we want to push into more knit-like structures and even woven structures. This is another super cool form, and this is a hierarchical lattice. So it's like there's a lattice, and then the lattice is filled with another lattice shape. These have really unusual mechanical properties. So actually Tom printed this, he mixed up some flexible resin and printed it. And then he said, I must have made a mistake. This thing is totally rigid. But it wasn't. He didn't make a mistake. It's just that the geometry actually makes this super strong, despite the material it's actually printed with. There's also possibility for a lot of thermal connectivity for something like a heat exchange application here, which we're exploring. And I've also challenged Daniel to a layer three-layer hierarchy of lattices. So stay tuned for that. This project, I think, is really similar in certain ways to the project that Emmanuel presented at the beginning. So these are spinoids, and this is a really cool metamaterial where the authors were trying to do something bone mimetic, much like what we saw earlier. And they too designed a machine learning model. They designed a forward model, and then this really nice inverse model that you give it a stress matrix and it spits out a lattice or several lattices that, or spinoids rather, that meet those performance metrics. I did get like really obsessed with spinoids for several months of last year, and I think I drove my colleagues crazy, but it amounted to some good stuff here. Okay, and so just to wind down, under the hood, I just wanted to say, what is this technology? We can think of this as a programmable shader pipeline to a 3D printer. We're always reading in the hardware state, generating geometry based on the hardware state. The computation is kind of done in layer time. So we have this kind of computation budget where we can do things as long as it doesn't take too long per layer, because any increase per layer amounts to a huge increase in the print time. We do things like implement the fast winding number. So we're able to print, really bad meshes by using the fast winding number. And we're able to do this because we're only looking at a small piece of geometry at a time. And overall, I think kind of more philosophically, this is the culmination of this observation we've been making from working in industry, that often people think they want to design lattices, but they actually don't. They actually want to like solve or optimize for some kind of solution. And so we really see this printer as being less about printing designs, so much as printing solutions to things. And so whether this is some kind of automated validation pipeline using a robot arm that takes your printout and physically tests it and then feeds the results back into your system, or whether it's solving some kind of differential equation on a per slice basis, or even reading in the chemical state of the resin for more sophisticated types of non-polymer printing, or just polymer variations. So in terms of the applications, I've talked a lot about mechanical metamaterials and lattices, and clearly we've done that. Kind of more generally though, you know, I think you are probably, many of you, in a very good position to think about what kinds of procedural geometries would lend themselves to this type of fabrication methodology. But there's certain things you can do procedurally that are just so much easier than in standard CAD workflows. An example is that hierarchical lattice, also things like adding noise or surface roughness. But even sort of more blue sky is, you know, the human lung. There's this fact about the human lung that if you unfold the surface of the human lung, you could cover a tennis court. So the surface area is enormous. And so obviously that's not something you're going to be able to print using like an STL or something like this, but can we capture that through an algorithm and print it procedurally? And so at this point, I just want to kind of extend an invitation that we're very much open and interested in collaborating with people, especially, you know, in the geometry processing community, who are interested in pushing the boundaries of the methodology. And I would just ask, how does shape matter to you, and how would you see this printing methodology? What would you do with it? So thank you very much for your attention, and I am looking forward to questions.
Thank you very much, Elisa. That was a really inspiring presentation. We've gotten, and proof of that is that we've gotten many questions for both of you, and we won't be able to get to, I think, even half of them. So I'm sorry preemptively to those of you whose questions I'm not going to ask. I'm going to post the link to our Discord channel on our YouTube chat, so that if you're seeing it right now or you're seeing this recorded, you can join a conversation later in case your question, we can't physically get to ask your question. Okay, but I'll stop. Let's ask our first question for Emmanuel while Elisa can have a glass of water or something. So your generative procedure for your bone structures relies on this adversarial neural network, when a neural network is learning to discriminate between real and fake. So a question that a listener had is, I wonder whether the generated bone actually shares similar structural properties with the real bone, or any other properties that are important. I take this to mean like, does it actually look similar or behave similar, or is it learning on the basis of some other property that we can't easily identify?
Yes, I just went quickly on that part of the paper because it's obviously more easy for us to appreciate the images and the renders of the 3D bone volumes. But actually, we ran as a more deep study where we analyzed the parameters which usually are common in studying bone. Those were the parameters I presented in one of the slides, but we actually measure how similar these new samples were to this overall space of parameters for real bone. And we actually only found one model which was capable to not only present visually pleasing and things that look like bone, but also they were indistinguishable from the parameter side on these things. Yeah.
Yeah,
but we didn't fabricate anything, so we don't. Okay. We actually don't have a printer for bone. So
that's like a collaboration waiting to happen here. Okay, let's move on to a question for Elisa. Okay, so you had your direct problem that you presented to us in the first half of your talk, and then you mentioned the inverse problem as a possibility. Some of us were thinking, can you just pre-simulate, like densely sample the space of lattices geometrically and combinatorially, and pre-simulate the simulation that you do, and then just simply do a lookup for which properties you want to have when you want to use one?
Yeah, and this is the point I was sort of trying to make, that that these lookups are not so easy to do, and like part of this is because when you have these different combinatorial types, how do you like, it's a discrete jump from one combinatorial type to the next. So how do you know kind of what direction to go in if you're trying to find like a nearest neighbor or something like this in this space of samples? So I think, yeah, it's not such a promising way.
I see. Okay, that's interesting. Okay, so another question for Emmanuel is, so from what you've done in your project with your collaborators, what steps do we need to have like a fully integrated deformation into 3D printing process, which feels more like in the direction of what Elissa was talking about just now, or Dr. Ross was talking about right now. What do you need to like fully integrate it and say, I want to print a thing that deforms this way, from what you were saying?
Okay, so we didn't went on that side. I mean, it should be, if you want to do like this inverse modeling of like you want a material with these deformation properties, and then you want to just say, computer, give me the material that actually do that. We are still far away from that, but I don't think it's that far. It's just that we didn't explore at all the deformation side because we were only focused on fabricating, on producing bone samples, which actually look real. But for sure, that's the next step, and we are looking into that. Yeah.
Okay, interesting. I'm just being convinced, more and more convinced to just thoroughly read your paper, Emmanuel. So I guess everyone else is having that to them too. Okay, so Dr. Ross, so if you shrink this model down enough, could you use the same pipeline that you do to design microstructure for medicinal purposes? Like for instance, if given a property that you want a drug to have, can you have a molecular structure that provides that property?
Yeah, I mean, that's a super good question. It's definitely outside of my realm of expertise, so I don't think I can really comment on that. But there is sort of one point that I swept under the rug a little bit, which is that lattices, you can kind of view them as either a structure or as a material. And so, and this gets to the idea of homogenization, where you're looking at a small sample and then you infer something about a larger sample based on what you've observed in the small one. But in some cases, and actually this is sort of more or less true for the machine learning model we built, we're really thinking of lattices as a structure. So we're looking at like fewer units of lattice. But I guess I don't see a huge difference. Like I think one thing we're really interested in is this sort of scale invariant property. So whether your lattices are a meter by a meter in like an architectural scale, or whether you're scaling them down to the size of a molecule, you know, what changes in that process? I think that's a really interesting question that I definitely don't claim to have all the answers to. But I think, yeah, it's something that would bear further investigation.
Thank you. Next question for Emmanuel. I have a set limit of questions I can ask. So the way I go around it is to combine 2 questions into one. So Emmanuel, here goes 2 questions. Okay. So combining a little bit from both talks, Dr. Yarusi, is there a use case for graph neural networks in modeling bone structure, just like Dr. Ross used them from materials? And related to that, have you encountered any infeasible generated results, so which I guess would be avoided using graph neural networks, like a piece of bone floating in the air or something like that? And how could we avoid those? So that's a loaded question. Go ahead.
Okay, so I can at least start it, and maybe Elisa can help me to finish it. It's a great question. I actually haven't thought of this problem as a lattice problem or graph problem. So after the Elisa's talk, I'm definitely going to rethink the way I'm planning to do next steps on this side. The thing, and now I'm asking Elisa, how can we? I'm not sure how can we. From your presentation, I got that the lattices you had are very like regular structures. So bone it's regular because if you look at a sample of bone, then you will clearly identify it as a bone, but it's not that regular. So how can you represent this randomness in the structure with your lattices? That's something I'm not really sure how to do it.
Yeah, that's an interesting question. I think I don't know. There's a few different ways I can answer this, but I think one of the downsides to lattices, I guess, is that they are so regular, and this actually turns out to be structurally problematic. So I know there's been some lots of work on bone implants actually using like triply periodic minimal surfaces and lattice type things, and they're problematic because they're so regular. Whereas in contrast, that Spinoid paper I mentioned, I mean, they have so few design parameters. I think it's 4 design parameters, and these then like stochastically generate an amazing bone mimetic structure that has like a homogeneous material property. So I would not ask, how can we make bones more like lattices? I would ask, how can we make lattices more like bones? So yeah, does that make sense?
Okay, that was a great answer from both. So we have another last question from Elissa, and then I'll ask a question to both of you. So at the beginning of your talk, you talked about slices of material properties, and we had this 2D plot of density versus strength. What other such slices are important, and can metamaterials help expand the material coverage for those slices too?
Yeah, absolutely. I mean, I think in the Panetta paper, looking at Young's modulus versus the Poisson's ratio or something like this, like there's any number of slices you can look at. And I know one of the kind of hot topics in metamaterials is these like smart metamaterials, where you actually have like a thermal property or some kind of shape changing property that happens on some trigger, like heat, unlocks a node and then it expands. And this is super interesting for even things like space exploration, where you have these kind of changes of state. So I think that there's sort of no limit to those kind of the relevance of those plots, and certainly any kind of, you might be interested in any pair of criteria, you can create this plot, and then absolutely metamaterials are going to help you think about how to expand into other areas.
That's really interesting. Very interesting specifically that you mentioned these types of metamaterials. It's a bit of a shame that we can only have 2 people in a session, and I want to use this to pitch next week's session, because we're going to hear from Professor Alexandra Ian, who has worked a lot on metamaterials throughout her PhD, and also from Athena Panatopoulou, who also works on tactile images. So like there's this session and next week's session are going to be very related. So if you're enjoying this one, make sure to tune in next week as well. Okay, so let's end with a question I had for both of you. Both of you have done interdisciplinary work, and both of you, maybe more than any presenter that we've had in this colloquium, have really emphasized the team aspect of your work. So you've both mentioned your collaborators in different fields of science, be it in art, be it in medicine, or be it in architecture. And the work you're doing goes a little bit different to what some of us are doing in academia, where we're really only working with people from our very same field. And sometimes it can be very hard to get accustomed to working with people from different fields, because we share different references, we share different goals. What is the general advice that you two can give to researchers, maybe starting their PhDs, maybe in their second year of their PhD at the University of Toronto, for example, that want to get into interdisciplinary research that's more practical, and what challenges should we expect and how to solve them? So let's start with Emmanuel Yarusi.
Okay, so just to be, I try to be short, but actually, I think all this interdisciplinary and very different work that you see that I usually am working on, it's direct. It's also, I mean, I like it, but it's also a consequence of doing science in a developing country. So that's something very important to say here. So I was, at some point, I did my PhD abroad in France, and then after a few years, I came back to my home country in Argentina, and we usually don't have that much resources. So I'm always trying to push my interest into the budget somehow. So now there is money for doing some things with bone. Well, I try to do bone geometry then. So it's kind of an opportunistic way of working in science, but it's the way it has to be in developing countries, because there's other ways you have to, I don't know, live outside. But that's and the secret for that, I don't know if I have any secret to share on this. It's just follow whatever you are actually interested in, and try to push in that direction, even if the money doesn't flow in that direction.
Thank you, Emmanuel. That's a very important perspective, and we're glad you bring it to this colloquium. I guess now I want to hear from Dr. Ross, who looks at this from the private funding perspective, not the public funding perspective. So I'm really excited to hear what you have to say.
Sure. Yeah. Well, yeah, I echo your comments, Sylvia. I think that that's a really interesting perspective that I wouldn't have thought of. So thank you for saying that, Emmanuel. So on my end, I don't know if I really have any generic advice for how to find interdisciplinary projects, other than just being open and receptive to these things. I can say that a couple of things from working in industry. So the first is about language. That I think this is maybe the biggest challenge in interdisciplinary work, is that you might be saying the same words and meaning totally different things. So the example that comes up all the time for me is the word topology, that this gets used in a million different ways. And I just try to avoid ever saying that word because people have different meanings for it. But so I think like that's a kind of key thing, is getting to the heart of what language means, not just taking it at some kind of immediate value. And then the other thing is that people often, in my experience, they come to you with a problem, but it's not actually the problem. So a big part of my work is to actually identify what the problem is that we're trying to solve. And this is another challenge, I think, in interdisciplinary work, is that getting started and defining the problem. And luckily, mathematicians and people like trained in geometry and stuff are good at kind of breaking things down and trying to really identify what the key things are that are unknown and need to be addressed. So those are the two things I would say.
Thank you very much. I definitely will take that into, I mean, the hypothetical asker will take that into account. So that's it for today. Before we wrap up for the day, let's thank our speakers again for their time, as well as Dalbert Villarino, the artist behind this week's poster. We will see you all next Wednesday at 1 p.m. Eastern to hear from Professor Alexandria Ian and